So why is this important? So there's a chart here that says we can obtain a theoretical optimum performance level. And then down here we have a minimal performance level. It says we've got to achieve certain levels from our infrastructure at this, otherwise we begin losing money. Everything in between these two lines is probably where the reality lies. So what happens is that once we implement a new box represented by this black line, our performance level basically we kind of get a little bit of an uptick as we optimize the machine, and then it begins to degrade with normal maintenance. It just the system will not be running the way we want it to because the application will begin to overload. It gets a little slower, and there's no set time. We're not necessarily saying this occurs immediately in 3 months. This is just a figurative approach to showing you how this occurs. However, what will also happen is if we do not maintain the box properly, we do not put the patches, we do not refresh memory, those types of things, this red line begins to take effect, and this is the performance degradation that occurs with reduced maintenance. Now, what will end up happening is that on the maintenance side, our maintenance costs, basically we have a little bit of spike because what will end up happening is that our overall cost is going to spike up at the beginning as we figure out how to better do this box, or how to better tune the box. It then drops at some point, and then eventually the costs will go, and again, these lines of minimal performance, optimal performance are for the left side, not for the right side of the maintenance cost. Our overall cost will then begin to increase as our performance degradation decreases. And the reason for that is because it will take more time. There are more patches, there are more requirements, and so there's usually more labor, or there's more things that need to be added. This green line actually basically says that similar to this, if we don't maintain our items, we will actually increase our costs because this is representative of unscheduled downtime. You will have more unscheduled downtime, you will have adverse performance on the applications, and therefore you run into a problem. Sometimes it's quantifiable, other times people will argue that it's not. I can argue that it always is quantifiable. The delta between these two lines here is the loss in the service life. So that if we're not maintaining this thing properly, the storage or any of these other things, we're ultimately going to figure that we need a new box, and therefore we will not optimize the box or the servers that we had obtained. And so this kind of represents the loss in service life, because once we get to the minimum performance level, if we're not maintaining it, the trend is to just throw it away and get a new one. So a lifecycle model might look like this. We basically put new equipment in that meets service levels into production, and this is the first phase of the life cycle. Then over time, we might rotate that equipment back into quality assurance. Then over time, we will then rotate that back into development. And while I'm showing a line here back into production, we really do not put that same equipment back in production. We just say that the cycle goes back to production where we will get new equipment. This equipment will get cycled out, usually to green waste management, or they could even be used for research and development on certain applications or something else. The benefits of doing this is you can decrease your downtime. You can obviously get greener IT applications because now you're managing your footprint much better. You can reduce your power consumption if you do this well. You can have a smaller footprint because technically if we do virtualization, we can take advantage of those types of technologies. Non-critical environments are kept close to par. As you can see, as we rotate this to quality assurance, well, quality assurance is not a critical environment as production is, but it does have importance. So the servers and the equipment that's actually put into quality assurance is fairly close to what would be in production. And development a little bit further away, but it also is ultimately going to be fairly close to what was in production, say a few years back or 2 years back. Something that can be easily used and managed. So as I said, the steps are, you conduct a technical architecture and inventory review. This means we catalog everything that we have, we understand all the various components, and then we begin to identify the outliers and understand where the gaps are and what we need to keep or what we can get rid of. We then establish the service level metrics. We ensure that what is expected by the business is what we are going to deliver. And these have to be agreed upon levels. Left up to the business would say we want 100% uptime. It's not realistic. It's also very cost prohibitive to do. And once the costs are put towards the business, they might say, well, we'll take a little bit less. We implement this rotation strategy. Now, the rotation strategy should be transparent to the business. They should never understand, or they should never, see any effect by rotating servers from point A to point B or point C. However, they should notice it in reduced costs and the less of a need to buy new equipment for non-critical environments. And then we provide the periodic cost analysis of infrastructure. The purpose behind this is to be disciplined about how we approach our IT operations. Some of the measures that we would focus on, external measures, as your book puts out, system uptime, response and turnaround time, program failures. Internal measures might be computer usage as a percentage of capacity, disk storage use, job queue length. There might be a more robust classification that organizations use, and organizations do use their own classifications. In fact, on the next slide, there's a software called Nagios, which is an open source system, and they can collect a number of statistics in 12 different categories, from CPU usage and load to memory levels to even processes. And all of these items are collected and stored in a database that can then be reported on. And it's these types of systems that IT operations folks use to ensure that the environment is running at peak capacity. This is an example of a Nagios report. This might be a dashboard that someone might use. And they would see, oh, we've got spikes in CPU time. And they seem to occur at a certain period of time. Now, this may be normal, and that may be acceptable, or maybe it's not. If it is acceptable, what we want to ensure is that these spikes, we understand why these spikes occur, and we also understand that our capacity level here is at 75%, that it doesn't exceed that. So we're not hitting a threshold of, say, 95%, where the CPU is completely utilized. Here on the network, I believe this is gigabits. Types of socket connections in use by the server. By the server is the color. This is the number of gigabits. You can see what's being used at the various levels here. Total memory, we see a spike occurring at, this looks like 11 a.m. And again, we might infer some things from these items. And you're always looking for the spikes. You're looking for things that are out of the norm. And then you try and explain them.